So here's my name, and I'd like to take the organizers for inviting me. And so I'd like to present my calculations of the energy in the relativity theory. So in the first part of the talk, and this is based on published papers. In the second part, I'm talking about cosmological applications of all these things, based on the paper that appeared yesterday. So I must say that to compute the energy is not easy. It's really long and technical computation with lots of details. And I'm going to skip all this and just show you some ideas. And first of all, let me summarize already now my conclusions, and I'll do it later again. So I find that the energy in the GT theory is positive for globally regular and asymptotically flat deformations of Nordita space. However, there are also other solutions of constrained equations for which the energy can be negative and even unbounded from below. However, it turns out that these solutions are either not globally regular or not asymptotically flat, which means that they belong to a sort of an orthogonal sector. So there is a positive energy sector and negative energy sector, and in a sense, the matrix elements of transitions between the two vanish. Therefore, the existence of these states should not be considered as a bad feature. And in addition, these states also contain the superluminal propagation. They're also there, but I think they all decouple.
So you're sure that the good sector doesn't have any superluminal?
I think so, yeah. Because superluminal states have negative energies. That's it. But again, it's not a proof. I do not prove anything. I only show results of my calculations. So, how do you compute the energy? So here is the theory. In the standard parameterization with the square root. So the Lagrangian contains the Einstein field part and the potential, which is made of eigenvalues of the square root matrix. And there are arbitrary parameters beta 0, beta 1, and so on. Now, how to compute the energy in the theory? Well, in the literature you can find some descriptions. Essentially, some people say that everything boils down to general relativity. This is not true. The correct way is to use the canonical analysis. And, well, I know that there are specialists in this room on canonical analysis, and there are many places where you can read about this. I myself personally found extremely useful the work of Volkov and Rachel Rosen, where they compute the secondary constraint. And also the group of the Italian group, whose representative Luigi Nesti is in this room. And this is a very systematic approach. They compute all constraint, primary, secondary, and so on. But I use the first one because this is simpler. Okay. So what to do? We have the Lagrangian here. Yeah? And then the first step is to do the standard 3+1 ADM decomposition of the physical metric. So the physical metric is parameterized, is split like that, and there is a three-dimensional metric gamma, and then there are lapse and shift functions n. So here are the variables in the theory, gammas and n's. Whereas the reference metric is chosen to be just flat, which means in the unitary gauge, ordinary. And then these parameterizations, the Lagrangian assumes the standard form. So there is a part which is exactly the same as in general relativity, which is expressed in terms of the second fundamental form. And also there is a potential term, which is proportional to m squared, and this potential depends on gamma and on lapse and shifts. Okay. The next step is to compute canonical momenta, conjugate these variables. And they are defined in the standard way. One has to vary the Lagrangian with respect to the q dot. And this gives non-trivial results for gamma. So there are momenta conjugate for gamma. But there is nothing conjugate for n. So the corresponding momenta vanish because the Lagrangian does not contain n dot. So the conclusion is that the variables n are non-dynamical. And dynamical variables are only gamma and pi, and there are altogether 12 of them. And they span the phase space, so the phase space is 12-dimensional. The next step is to construct the Hamiltonian. The Hamiltonian is in the usual way is p q dot minus L, and this assumes this form. And the first piece is the same as in GR. So it's a linear combination of n's with this h, which I given here. And also there is a potential term which is u multiplied by square root of minus g. It's called v. And the potential depends on the metric and also on the non-dynamical variables. And now there is an important condition. Since these momenta conjugate to n vanish, their derivatives should vanish too. But the derivatives in the Hamiltonian description, p dot is dh over dq conjugate. Therefore, this combination should vanish. These combinations are reduced to the following one, and these are four conditions, four of them, which determine the number of propagating degrees of freedom in the theory. This is important. So first, let's see what happens if you choose m to be 0. If m1, if m is 0, then we are back to GR. And in this case, we have four vanishing quantities, and they depend on p and q, and therefore these four quantities have four constraints. And if one computes the mutual Poisson brackets, one discovers that they form an algebra, and therefore they are first-class constraints, which are generators of diffeomorphisms, of symmetries. And for each generator, one can impose a gauge condition. Therefore, the number of degrees of freedom is 12 minus 4, number of constraints, minus 4 gauge conditions. There remain 4 phase space variables, which correspond to 2 gravitational polarizations. So this is a standard counting. And the Hamiltonian, it's just a linear combination of constraints, and therefore it vanishes on the constraint surface, up to the boundary term. In GR, there is a massless mode, which gives a Newtonian tail, and in order to make sure that the variation of the Hamiltonian is done correctly, one has to add boundary term, which cancels some boundary effects. Yeah. But not in massive gravity. In massive gravity, everything is recovered. You see? So one doesn't need it. So next, let's return to this, and let's consider the case where m is not 0. In this case, one gets 4 conditions, and they contain p, q, and also the lapse and shift functions n. And these 4 conditions can be viewed as equations for laps and shifts. However, they do not determine laps and shifts, they determine only shifts, only 3 shifts, because the Hessian matrix for this potential has rank 3. And this is the whole point of the Gauss stream of massive gravity. Rank 3 means that one can determine only 3 of them, not 4 of them, only 3. So one finds 3 shifts from the 3 of these equations, and if one then plugs the 3 shifts into the 4th equation, the lapse cancels identically, and what leaves is a constraint. Is a constraint which depends only on P and Q. And the Hamiltonian assumes the following form. There is a something plus constraint plus the lapse times the constraint. Now, the constraint should be stable. And the stability condition is that the commutator with the Hamiltonian should vanish, and this gives the secondary constraint. If one continues this procedure, the stability of the secondary constraint does not give new constraint, but it gives the equation for the lapse. Therefore, there are two second class constraints, and this reduces the number of phase space variables to 10, and which corresponds to 5 polarizations of massive gravity. So here is the count. And then the energy on the constrained surface is just this. Yeah. Now, here is the energy density. But now the problem is that in order to compute it, one has to first resolve the constraints. One has to go on the constrained surface and only then compute this. And which I believe in principle is simply not possible. Because the constraints are extremely complicated partial differential equations, and moreover, they are not even known explicitly. Because in general, even this is not known explicitly for arbitrary values of the parameters. You simply cannot resolve these equations with respect to the shifts. So, what to do? Not much. Well, my, great invention was this. You go to a spherical symmetric sector, and then you can do something. Well, in GR, there is nothing in spherical symmetric sector because there is no dynamics. Whereas in massive gravity, it's not the case. In massive gravity, there is a scalar graviton which propagates in the sector, so you can find something. And therefore, you impose the spherical symmetry, and we choose our metrics in the following form. So now the G metric contains 4 metric functions, n, delta, beta, and r, where n and beta are lapse and shifts. They are still non-dynamical. And there are 2 dynamical variables, delta and r. R is a Schwarzschild radius. And they are functions of two coordinates of t and r. Yeah. And then again, there are no momenta conjugate for lapse and shift, but there are momenta conjugate for delta and r. And so phase space is 4-dimensional, 4 variables. With this, one does the Hamiltonian in the standard way, pq dot minus L, and one gets this expression. And there are quantities H0 and HR, which were computed long ago by many people in the 70s. There was activity on spherical symmetric quantum gravity. And the potential is explicitly given here. There is a square root. And there are quantities P's, which are polynomials with the coefficients dependent on these parameters B and P. Now, one does again variation. One varies the Hamiltonian with respect to lapse and shift. And again, if m is 0, then this gives 2 first-class constraints, and the number of degrees of freedom, therefore, is just 0, which is a Birkhoff theorem. There is no dynamics in S sector. Now, if m is not 0, then the counting goes differently, because in this case, one can determine beta from the second equation in this way. And when one plugs it to the first one, then the lapse n disappears. It just cancels. And what remains is the constraint. And here is the constraint explicitly. It's this one. Well, where h was defined previously, y is the square root. And there are other things. The Hamiltonian is this. And the energy density, well, this is the energy density epsilon. Is given by the following expression. However, already this is so far it's more or less okay, but already the secondary constraint is it's quite a computation. So the condition of stability of this one, the commutator, it's not completely trivial to obtain this. And then the degrees of freedom is 4 minus 2 is just 1 degree of freedom. Then the energy is just the integral of this, assuming that the constraints are fulfilled. And so now what is to resolve? These constraints are ordinary differential equations, quite nonlinear but ordinary. So these are different differential conditions for 4 variables, and one has to solve them in some way. Well, in general way, I could not, but I was able to consider special cases. First of all, one can go to flat space, and one can check that if in flat space, everything is fulfilled, which means the constraints are satisfied, and the energy is 0. Now, suppose now that we are close to flat space, that we are in the Fierce-Pauli limit. So if the configuration deviates slightly from flat matrix, then one can expand everything, and then the constraints become linear, they can be solved, and then the energy becomes quadratic, and after some manipulations, it becomes a total square plus a total derivative. Perfect square plus derivative. Therefore, the energy is positive. So, which simply agrees with the fact that the Fierce-Pauli energy is positive. Okay. Now, let us do more than this. Let's consider the sector where the metric is flat, but the momenta are arbitrary, not small, just arbitrary. And then the 2 momenta, P delta and PR, can be expressed in terms of 2 functions which are called Z and F. And then the constraints boil down to 2 first-order differential equations. And the energy assumes a simple form. This is x, where x is the radial coordinate, dimensionless, times F, and F appears here. And here, for the first time, we see the negative energies. Because there is a square root of F plus 2, and the argument of the square root should be positive, which requires that either F is bigger than 0, or F is less than -2. So if F is bigger than 0, then the energy is positive. If it's less than -2, then the energy is strictly negative. And these are 2 branches, 2 solution branches. And, but if one plays a bit more, one discovers that there is something wrong with the negative energy solutions. First, there are some analytical solutions, but they are for these solutions, the function z always changes sign. However, there is a square root of z. And therefore, outside the interval where z is positive, the solution becomes imaginary. And if you do some numerics, then the result is even worse. One can see that the solutions are typically exist only on compact domains, and they're singular, barely singular. Whereas the positive energy solutions are okay. They're smooth and Now, let me continue and consider. Yeah.
What happens if we add a constant with a positive and negative?
Cosmological constant is there. It is contained in the parameters of the theory. There is a parameter. Parameter beta 0. So u is because u plus v1 times lambda plus. So this is like a cosmological constant.
It doesn't change the.
Must be a constraint that you're imposing on the parameters in flat space as a solution.
Exactly. Well, exactly. So I always do this. Yeah. So I say so. These are k are functions of alpha c and alpha 4. Okay. So now I consider another case where momenta vanish, but the metric can be arbitrary. So the 2 metric functions, delta and r, I express them into others in terms of g and h. And then the secondary constraint is identically fulfilled, whereas the first one, the primary, gives this differential condition for 2 functions, for h and g. And in order to get asymptotically flat solutions, one has to require that h goes to 1 at infinity. And then the energy density is this. And one discovers special solutions. So if h is equal to g is equal to 1, then this is flat space. And then the energy is 0. This is A, but there is another solution. If H is equal to 1/2 and D is 1, then this configuration solves the constraints and also solves all the Hamilton equations, all of them. So this is the exact solution. But these solutions, both metrics are flat, but with the proportionality coefficient. This corresponds to the case where alpha 3 and alpha 4 vanish. And the energy density is strictly negative. And then the volume energy density, just volume is constant, negative and constant, which means that the energy is just minus infinity. And if one computes the first Pauli mass of the graviton, then it is imaginary. So, and therefore I call this tachyon branch. So again, there are two branches. Then one does fluctuations around this and around this. So if I perturb the positive, so the first branch, I can essentially find all solution. Well, I can reduce the constraint to algebraic equations. And then solutions are smooth, globally regular, asymptotically flat, and the energy is always positive, always. So in all cases I consider it is positive. It's not a proof again. But this is all I found. Positive solutions in this sector. For the other branch, the energy is always negative, and it's always infinite, negative. But here is the following observation. They look unpleasant, I agree, but they cannot affect the positive energy branch simply because they have different boundary conditions at infinity. And so it costs infinite energy to deform this to this. And if one starts, one can try, if one starts deforming this guy to this guy, energy quickly goes, then it shows the pole, and emerges from the other side from minus infinity and approaches a negative value. Therefore, there is infinitely high potential barrier between two sectors. They are disconnected. However, there is then I discovered something really unpleasant. So I found solutions which are asymptotically flat and interpolate between the two branches, which start from the tachyon phase at the origin and approach the flat space phase at infinity. This, yeah, 1/2, and then and then the energy is negative and finite. And so they describe a sort of a bubble of the tachyon phase. So there is a tachyon phase inside, and there is a bubble, and asymptotically flat. So I was really embarrassed, and I thought that this was the end of the theory. But then, after some analysis, I realized, so they look perfectly regular. But I realized that the shift function is singular for these solutions. Not always singular. It shows a pole, even many poles. So in some cases, I was able to prove this. In other cases, it was just numerical evidence. Since they are singular, they cannot be used as initial data for a decay of flat space. So they are something disjoint. Yeah. So the conclusion is that negative energies are harmless. And so let me summarize the first section. The energy in the theory can be positive for globally regular and asymptotically flat fields. It can also be negative, but only in the case the fields are either not asymptotically flat or not regular. And I think my interpretation is that these fields, they form a sort of a positive energy sector, a healthy sector, whereas these guys, they have negative energy and they have tachyon features, which means superluminalities and all that, but all this exists in the orthogonal space. It doesn't influence the physical sector. So again, this is my interpretation. I cannot prove it. It would be great to really prove a positive energy theory. It would be just great, but I don't know how to do this.
Okay, so this fall in the labs you found, is it coordinate singularity?
Oh, no. No, it's not a coordinate singularity, it's no.
This is unitary phase.
Yeah, it's everything, the gauge is fixed. It's unitary gauge. If n varies, which means the momentum, the p dot divergence. So therefore, the initial data require the infinite momentum. This is not good. And now, my next purpose was to try to apply this to the stability of cosmology. And this is based on yesterday's debate. And the cosmology, I repeat, the cosmology in the massive gravity theory. So let me summarize what is known about cosmology, not what is known, the general situation. The situation, in my opinion, is the following. People think that the theory does not admit spatially flat, homogeneous and isotropic cosmologies. One thing. There is a spatially open, homogeneous and isotropic, but it is unstable. And on the basis of these two things, people think that the theory should be abandoned. And therefore, people, well, more or less, people now do quasi-dilaton, you know, other things. But nobody really studies this. But I'd like to emphasize that the theory contains infinitely many different cosmological solutions, infinitely many. And they were not studied only one, not even several, not even two, only one. Only one solution. So these two solutions are the same. I will show this in a moment. This is just one solution. And only one solution has been studied. And all on the basis of negative evidence obtained from just one solution, the whole theory was actually rejected.
We studied Bianchi 1 too.
No, I'm talking about
anisotropic
treatment. Okay, but I'm talking really about this. Well, there are some solutions, of course. And in bigravity, it's by the way the same situation. People study just one solution, essentially, one branch, and then they will soon reject the whole bigravity just because of this. So let me see what is really known about cosmologies in the theory. It is known that the field equations admit de Sitter solution. By cosmology, I mean, let me just de Sitter. So there is no matter, it is pure de Sitter. De Sitter solution. And this is the physical metric. And the reference metric depends on the Stuckelberg scalar, which fulfills a very complicated nonlinear partial differential equation. Well, it's not really clear how to solve this equation, and most people don't even bother to solve it. They assume that solution can be found somehow. But again, since it's a PDE, it has infinitely many solutions. And these solutions have different physical properties. One should study them before the theory, before rejecting the theory. And so everything was reported in many papers. And now I'm going to show you that this equation can be written in a very simple way, and it is essentially a general solution. So I'll present you a general solution. So first, let me remind you that the Sitter space can be used as a hyperboloid with a radius alpha in a 5-dimensional Minkowski space with a standard metric. And this geometry induces on the hyperboloid the de Sitter geometry, and the de Sitter geometry fulfills the 4-dimensional Einstein equations with a cosmological constant lambda, which is related to the radius in the following way. Okay, this is a fact. And then one can consider different coordinate systems. One can rewrite this metric in a cosmological form. By changing coordinates, one can write the metric in a form of expanding cosmology, which can have either flat or spatial or closed or open or closed spatial sections, depending on the choice of coordinates. And also, there are coordinates in which the metric is static, because the Sitter space admits a time-like Killing vector, even though not globally, but locally. It is time-like only in the finite domain inside of the Sitter horizon, but still it is static. Now, how can we use this information in order to obtain something in massive gravity? In massive gravity, there is a very interesting thing called golden ansatz. This is proposed by Patricia and colleagues in this paper. And the thing is this. It is enough to make sure that the two metrics G and F are related by this condition, where omega and zeta are functions, and V is a time-like unit vector field. And if, in addition, this omega is a constant, which is the root of a quadratic equation, algebraic equation, then one can immediately show that the energy momentum tensor is proportional to the unit tensor, with the proportionality coefficient given here, and therefore the physical metric is an Einstein space. So it's enough to, one can also check all equations one by one, which is long and boring. This is much faster. And then the coordinates are used, the global embedding coordinates are extremely well adapted for this kind of calculations. So what does the following? First of all, in these coordinates, so one parameterizes the de Sitter space, as I said. Then the reference metric is chosen like that. So it contains a manifestly flat piece plus differential or function squared, and this is the Stuckenberg field. Okay. Then one can immediately see that the difference between the two metrics are related as follows. That is sum of differentials, and this will be compatible with the Gordon ansatz if these three guys can be expressed in terms of unit vector field in the following way. And it's a trivial algebra to see that this is possible, provided that T satisfies the following consistency condition. This one. And this is the equation I announced. It looks very simple. However, if you try to go to other coordinates, it becomes extremely ugly, just extremely. With no hope to solve it. Here it's everything simple. And the general solution is available. Oh, people, of course, don't care about general solution. So let's consider the simplest. The simplest way, simplest solution, is T large is equal to T small. So this isn't it? Now let's take T large equals to T small, and let's transform this solution to some of the known coordinate systems. So let's first choose the flat slicing. For flat slicing, the relation between the embedding coordinates and the flat coordinates are given by the following expressions. And then the metric becomes the standard Friedman-Robertson-Volkov with the flat special sections, where the scale factor is exponential, so it's really it's inflation, you know. And the reference metric becomes this, and here T can be expressed, T, which is large, which is small t, can be expressed in this way. And this is exactly the solution found in this well-known paper. Exactly the same. And, well, if you look at T, then it looks, it depends on rho. So if you plug it back, then the reference metric becomes rho dependent and non-diagonal. So it looks unpleasant. And therefore, the natural conclusion is that the metric is inhomogeneous. So there is no, and then the people say that there are no homogeneous and spatially flat cosmologies in the theory. Okay. But now let us return to this parametrization, and let us transform it to open slicing. And the transformation is given by these functions, and then we discover exactly the famous solution obtained by the group of Shinji Mukayama, which is manifestly homogeneous and isotropic. Manifestly. Which means it has translational and rotational isometries, so altogether 6, and which is considered as the only homogeneous and isotropic solution in massive gravity. But attention, this is exactly the same solution as before, right? No? For the solution which we had before also has 6 Killing vectors. Also the same, because the Killing vectors, isometries, exist independent of the coordinate system, right? So therefore, this solution is also homogeneous and isotropic, even though its translational symmetries are not these translations of this. These are hyperbolic translations. But still it is also homogeneous and isotropic. The lesson is that two metrics can have common isometries in a non-manifest way, which is not obvious. So they're not seen, but they're common. Yeah. So one cannot just reject solution because it does not look homogeneous and isotropic. This is not true. However, now the last thing, let us try to transform again the same solution to static slicing, to the static. If you do this, then the de Sitter space becomes static. It doesn't depend on time, whereas the reference metric unfortunately remains time dependent. So there is a T here, and so the solution is not static. And I believe this is the reason why this solution was found to be unstable, again by a group of Sinji-Mukhanyan. Because I think if it was stable, it would describe a sort of a ground state in the theory, but the ground state is normally static. You know? Therefore, I think this is the underlying reason. So again, this is about normal solution. No. All this, in my opinion, means that we should consider other solutions of this differential equation. So what are the other solutions? Well, all of them are here. The fairly general solution containing an arbitrary function w of psi is given, is expressed in these two lines, where the second line implicitly determines the dependence of psi on t and r. So I think these are, if not all, but almost all solutions. But the problem is that it is difficult to use this formula because it's difficult to resolve the second line with respect to psi. Other methods, there is a well-known method of characteristics. So the method is this. Let's consider TR in Minkowski space and an arbitrary curve such that T is constant on this curve. At each point of the curve, there is a unit time like normal, and then the equation is equivalent to this statement, that the derivative along the normal is 1. And this allows us to extend the values on the curve everywhere in space and gives a solution. And it shows that the solution is uniquely up to the constant E is defined by a choice of the curve. A practical method is to use separation of variables. One can transform the equation to some other coordinates and then separate the variables, and this gives interesting solution. And in particular, my suggestion is that one should use static solutions. Solutions for which dt does not depend on time, and therefore the reference metric is static, and therefore the whole solution has a time-like isometry, both metrics. And all static solutions are written here. And now I think they are candidates here. And now I want to compute the energy. So, by the way, they also can be expressed in the following nice form, the static solutions. And only for these solutions, the energy is time independent. This is very strange. So all other solutions, infinitely many of them, have time-dependent energy. And then the energy can be again defined, constructed by the canonical methods, even though it's a little bit involved for non-trivial Schickelbergs, but it can be done. And then there are also constraints and all that. I do not show this, I only show the final result. If there is a solution, which is on shell, so the constraints are fulfilled, then the energy density becomes very simple, and it is in the static slicing, it is proportional to the derivative of large t with respect to small t. And if you take this simplest solution, known solution, then the energy is time dependent. So it's sort of, there is a kind of external field here. So again, I think this means that it cannot be a ground state. Whereas if this thing does not depend on time, then the energy density becomes constant, which corresponds to a constant energy density. And now I make a conjecture that these solutions are stable and that their energy is minimal. To show this requires some, this is the same as for stability of Newtonian space. All these deformations and constraints. But if this is true, this solution will be, you know, real, describing real, the ground state in the theory. So I think the theory, well, the theory was invented for describing this, just for this. And there should be ground state in the theory. There should be a hyperbola and it should be stable. So this is my point. But again, this is conjecture. And so my conclusion is that, conclusions are this. In the GT theory, there are infinitely many de Sitter solutions labeled by a function which fulfills this differential equation. Solutions can be homogeneous and isotropic, which means that two metrics have common rotational and translational killings in a non-manifest way. And there is a one-parameter subfamily of the solutions for which both metrics are static, and the energy is time independent. And the conjecture is that the energy is minimal. But this is the conjecture.